Hello class, here is the question 3 on collision theory. The question says, the figure below shows a flywheel A connected through a torsional flexible spring to one element C of a dog clutch. The other element D of the clutch is free to slide on the shaft, but it must revolve with the shaft to which the flywheel B is keyed. The moment of inertia of A and B are 22.5 kilogram meter square and 67.5 kilogram meter square, and the torsional stiffness of the spring is 225 Newton meter per radian. When the flywheel A is revolving at 150 RPM and the flywheel B is at rest, the dog clutch is suddenly engaged. Neglecting all losses, we have to find 1. Strain energy stored in the spring. 2. The maximum twist of the spring. And 3. The speed of flywheel when the spring regains its initial unstrained condition. Now let us look at the solution to this. Now let us look at our given. Here we are given the moment of inertia of the flywheel A, which is IA, is given as 22.5 kilogram meter square, and we are given the moment of inertia of the flywheel B as 67.5 kilogram meter square. We are also given the torsional stiffness of the spring. Let us use Q to represent this, which is equal to 225 Newton meter per radian. Then also we are given the speed of the flywheel A, NA, as 150 RPM. Converting this one to radian per second, we have the angular velocity to be 2 pi NA over 60, and this will be 2 pi multiply 150 over 60, and this gives 15.71 radian per second. Now, you know that immediately after the clutch is engaged, the element C of the clutch comes to rest momentarily. It will come to rest momentarily, but the rotating flywheel A starts to wind up the spring, and this causes equal and opposite torques to act on flywheels A and B. The magnitude of the torque increases continuously until the speeds of wheels A and B are equal. And during this interval, what happens is that the strain energy is stored in the spring. And after this, the spring starts to unwind, and the strain energy stored in the spring is converted into kinetic energy of the flywheels. And here, since there is no any external torque that acts on the system, therefore we can say that the angular momentum will remain constant. So if we say let omega be the angular momentum for both flywheel at the instant their speeds are equal. So is the angular momentum of both flywheels at the instant their speed are equal. Then from here, writing the momentum equation, we have the total momentum before the impact is equal to the total momentum after impact. We have IA omega A plus IB omega B, then is equal to, since they move off with the same angular velocity, they will now have IA plus IB multiplied by their common angular velocity. But we know that flywheel B is at rest, so this will be 0. Then we now have IA omega A is equal to IA plus IB multiplied by their common angular velocity, making this the subject of the formula. We have omega is equal to O IA omega A over IA plus IB. When we substitute the value we have 22.5 multiplied 15.71 over 22.5 plus 67.5. We are going to have 3.93 radian per second. The kinetic energy of the system at this instance, that is when the speeds are equal, can also be obtained. Then let us look at the initial kinetic energy of the flywheel A. Because flywheel B is at rest, so it possesses no kinetic energy. So kinetic energy of the flywheel A, let's call it E1. Then E1 is going to be a half IA omega A square. So when we substitute the value, we have a half multiply 22.5 multiply 15.71 square. Then we are going to get 2776 Newton meter. Then let us now calculate the kinetic energy of the system when the speeds are equal. So, and we'll have that one as E2. Then it will now be a half IA plus IB multiply the square of their common angular speed, which is equal to a half into IA, which is 22.5 plus 67.5 multiply 3.93 square. When we evaluate this, we are going to have 695 Newton meter. Now, let us go and calculate the strain energy stored in the spring. We know that the strain energy stored in the spring is going to be the difference between these two energy, which actually is not lost, but it's converted into strain energy. So the first question, strain energy in the spring, so is going to be equal to E1 minus E2, so which is equal to 2776 minus 695, and this gives 2081. Newton meter. Then the second question there, we have to calculate the maximum twist of the spring. So let theta be the maximum twist of the spring in, let's radian, and we know that the torsional torque is K. You say K is the torsional torque or torsional stiffness rather, stiffness of the spring. And we're already given as 225 Newton meter per rad. Then from here, we know that the strain energy is equal to a half Q theta square. And the strain energy, we have calculated it to be 28.1, which is equal to a half multiply 225 multiply Q square. So when we evaluate this, we have Q square is equal to 2 multiply 2081 divide 225. Then theta will be equal to the square root of 2 multiply 2081 over 225. And this gives 18. And this gives 4.3 radian. And converting this one to degree, which is equal to 4.3 multiply 180 over pi, and this gives 246.3 degree. Then the third part of it, we have to calculate the speed of each flywheel when the spring regains its initial unstrained condition. So let NA1 and NB1 be the speed of the flywheel, A and B respectively. When the spring regains its initial unstrained condition. Then from here we know that this relationship NA1 is equal to 2N minus NA, and this will be equal to 2. So our N in radian per second is given as 60 multiply. Our N is given by 60 multiply omega over 2 pi, then minus NA. So which is equal to 60 multiply 3.93 over 2 pi multiply our NA is 150. So, and this gives 75 minus 150, which is equal to minus 75 RPM. And then Similarly, then for the flywheel B, we have NB1 is equal to 2N minus NB. So which is equal to 2 multiply 60 multiply angular velocity over 2 pi minus NB, which is equal to 2 into 60 multiply 3.93 over 2 pi. And NB is 0. And when you evaluate this one, this gives 75 RPM. From the above, we can see that when the spring regains its initial unstrained condition, the flywheel A will revolve at 75 RPM in the opposite direction to its initial motion. That's why it is negative. While the flywheel B will revolve at 75 RPM in the same direction as the initial motion of the flywheel A. Thank you very much for listening.